Hello, everyone, and welcome to our webinar today. The topic for today's webinar is Informing Energy Storage and Storage-Enabled Microgrid Project Decisions using EPRI's StorageVET. This webinar is being presented by the DOE-OE Energy Storage Technology Advancement Partnership, also known as STAP. STAP is a collaboration of the U.S. Department of Energy Office of Electricity, Sandia National Laboratories, and the Clean Energy States Alliance. Before I pass it over to our really exciting panel of speakers, I'd like to go over a few very quick webinar logistics. All of our attendees are in listen-only mode. You have a couple of options to join the audio portion of our webinar today. You can call in via telephone or connect via your computer, mic, and speakers. If you'd like to minimize your webinar console so that you can view your presentation full screen, you can click on the little orange arrow that you see circled here on the slide. And you can also click on that arrow to expand the webinar console. One thing you might like to do with your webinar console is to submit your questions and your comments. After our presentation and demo today, we're going to have a Q&A with the audience. We've got a really great panel here to answer your questions, so do type those questions and comments in as you think of them. A final note, this webinar is being recorded. We'll send you an email with a copy of the webinar recording within about 24 or 48 hours, and we'll also post those materials on CISA's website at cisa.org/webinars. And that's a great URL to know because it's also where we post all of our upcoming and archived webinars. So with that, I'm now going to pass this over to my colleague, Anna Adamson. Anna is a staff member here at the Clean Energy States Alliance, and she is moderating our webinar, and she will get us started.
Great, thank you, Sam, and thank you everyone for tuning in to today's webinar. Before I introduce our wonderful panel of speakers, I'm going to briefly provide some background on Clean Energy States Alliance, otherwise known as CISA, and the STAP Energy Storage Program. CISA is a bipartisan nonprofit organization. We offer membership to state energy agencies and other related offices. You can see the logos of many of our members on your screen now. We help them with developing clean energy policies and programs of all kinds. Next slide, please. Today's webinar is a part of CISA's DOE Energy Storage Technology Advancement Partnership, STAP. This work is conducted under contract to Sandia National Laboratories and funded by the DOE Office of Electricity. Within STAP, our work revolves around three main activities, which you can see on the screen. One main area of our work is hosting webinars like the one that we're having today. We host webinars to share information, amplify successful projects, and highlight useful resources like the StorageVET energy storage modeling tool that we'll be learning more about today. We also support state energy storage efforts with technical support, policy support, and program assistance. Our primary work within STAP is in partnership with Sandia and DOE-OE. We work with them to identify and facilitate the development of energy storage demonstration projects. These projects are jointly supported by state agencies, the federal government, as well as utilities and other private stakeholders. Next slide. Before we go any further, I want to thank Dr. Imre Zsuk, Director of Energy Storage Research at US DOE Office of Electricity, and Dan Borneo, who is the Engineering Project and Program Lead at Sandia National Laboratories. None of the work that was just described on the last page would be possible without them. Next slide, and on to our speakers. First, we will hear from Mike Gravely from the California Energy Commission. He is the team lead and senior electrical engineer for their Energy Systems Research Branch. His team is managing over $300 million in microgrid, energy storage, and related energy research and demonstration projects. After Mike, we will hear from Hadice Getchell. She is a commission energy specialist at the California Energy Commission. She oversees microgrids and short and long duration energy storage projects. She now has over 20 years of experience in renewable energy research and policy development at the state level. Next, we'll hear from Giovanni D'Amato from the Electric Power Research Institute. He serves as Principal Project Manager in the Energy Storage and Distributed Energy Resource Program. Giovanni has over a decade of professional experience leading the exploration of distributed energy resources, including grid-connected energy storage and microgrids. He is the Project Manager for the StorageVET energy storage modeling tool that we will learn more about today. After Giovanni, we'll hear from Ram Ravikumar and Miles Evans. They will be demonstrating the StorageVET tool for us today. They are both technical leads at the Electric Power Research Institute. Ram is responsible for energy storage and distributed generation deployment, implementation, and valuation analysis. He is also involved in microgrid feasibility analysis. Miles is involved in valuation, data analysis, and modeling efforts in the energy storage and distributed generation program. He works on simulating the operation of, valuing the effects of, and characterizing the real-world performance and reliability of energy storage systems. In addition to that wonderful list and lineup of panelists of speakers today, we will also have Andrew Ettringer from EPRI, who will also be joining us for the Q&A. Andrew is a software developer at EPRI, where he provides software support for EPRI's power, delivery, and utilization sector. He currently implements and tests modeling capabilities for EPRI's StorageVET tool. We are hoping to be able to reserve about 15 minutes for Q&A at the end of this webinar. So like Sam said, be sure to submit your questions and comments into the control panel as soon as you think of them throughout this webinar. In case we don't have time to answer every question during today's webinar, you can reach out to the speakers after today, and they've also agreed to review the questions submitted today and provide written responses to any that we weren't able to get to. Again, thank you everyone for joining today's webinar. The floor is all yours, Mike. He will be speaking to us. He is audio only, no slides and no webcam. So all yours, Mike.
Thank you, Anna, and thank you for inviting us and for having this presentation from EPRI. I just wanted to make a quick introduction. For those who don't know me, I'm Mike Gravely. I've been to commission for 20 years. I've been working in energy storage, microgrids for almost all of that. So this tool, we've been working with EPRI for about 5 or 6 years. We started with it as a storage-only tool, and then it became really a microgrid tool. The most important thing I wanted to mention to everyone was this is a tool that is funded by the Energy Commission and cost shared by EPRI. It is open to the public. There is funding for training and use for the tool. So those of you that are listening today that are interested, just be advised, you can reach out to EPRI. You can go on the internet. You can get technical support if you need to help you use the tool. Our goal is to make this as useful as possible. Our EPRI program has funded over 45 microgrids, and that's why we're using this type of tool to help us understand it. I will also add that we are in the process of doing an amendment to this tool to add long duration storage and to expand its benefits assessment to a broader range, so the tool will be even more valuable in the future. And again, I thank everybody for listening in, and I'll be here all throughout to answer questions later at the end of the session. But I just want everyone to know that this is being funded by the California Energy Commission. This is a publicly available tool. You can access it through the internet, and there is training and technical assistance available for any of the states that want to try to use this or to share this with their position. TJ is the project manager for it, so I'm going to pass it on to her and let her answer any additional questions and provide a little bit from there. But both of us will be able to answer questions at the webinar or any other time in the future. We really would encourage everyone to use it, because the more we use the tool, the more valuable it'll be for all of us. So thank you.
Thank you, Mike. Thank you all also for joining us today. I am the Commission Agreement Manager for this project and had the pleasure working with the EPRI team. I am here to answer any question you might have regarding our program after the presentation given by our EPRI team. And from there, I would like to pass the microphone to Giovanni. So please go ahead.
Thank you, Hatice and Mike, for that great introduction. We are excited today to talk with you about the StorageVET tool and kind of walk you through some live demonstrations during this webinar. So if we go to the next slide. All right, perfect. All right, so what I like to do is, start out with, why we're here and doing this. I think Mike started out with a great introduction, but now getting a little bit more into the details about what are the challenges we're trying to address here. I think most of you on the phone know that energy storage, DER, and microgrid modeling can be pretty challenging, and this tool kind of fills those gaps, hopefully, and really helps with making informed decision making for strategic planning for across a broad range of stakeholders, from customers trying to make decisions about putting in storage and microgrids, utilities, technology providers, people doing deployment in the industry, and also regulators as well, trying to understand how to integrate these types of projects onto the grid, and potentially how to incent them as well. Another piece is that valuation of storage and microgrids requires project level application and locational analysis. So DerVET focuses on the project level and really gets into the weeds, and we'll demonstrate that. Another piece is, with energy storage, you can tell it what to do. It's not passive. So there's a complex co-optimization and decision-making process to go through during planning, design, and then of course in real-time operations. And the DerVET tool, we hope along the way, has addressed those challenges, and we continue to improve the tool to keep up with the needs of industry and stakeholders. So we mentioned that the tool is open source, and it's focused on understanding energy storage, DER, and microgrids on their technical merits and the constraints, and how they provide benefits and grid impact, and look at the total cost benefit analysis of particular projects that you're looking at. And because it's open source, it is a common communication tool that all stakeholders can use to define issues on the grid, and for customers, how to address those with the various technologies, and then see what those results are in terms of economic, technical impact, and other impacts as well. And we developed DerVET. It has the DER distributed piece to it, but we designed it so that you could look at putting these DERs either customer sided, distribution connected, transmission connected, or generation sided, in hybrid applications as well. And that includes DERs, energy storage, and microgrids. So our hope is that we can be inclusive with this tool, and we've demonstrated that, I think, by the fact that we have over 1,000 users now of the tool. We released a beta version in 2020 and the full version in 2021, and now over the past year and a half, we've continually improved with updates and new features as we get feedback, and we'll talk about how you can engage in that feedback on a continual basis a little bit later. And also, there's a long history of our modeling development, starting back over a decade ago, and also the predecessor tool to DerVET, which the Energy Commission also funded, which was StorageVET, which is basically still the core guts of DerVET optimization today. We're going to dive into some demonstrations, so I don't want to go into too much here. Just to say that Miles is going to go through a particular use case in the tool, and we'll use the graphical user interface to configure it, to talk about the results, and hopefully answer your questions in real time and get some good engagement. And in this particular case, I'm not going to go through this whole single line kind of diagram here, but we're going to focus on battery energy storage today. and specifically flow batteries and long duration. And there's a lot of different services available for energy storage and microgrids, depending on where they're located and what kind of capabilities the technologies have. But today we're going to look at a New York case where we're using a longer duration energy storage system in New York to do energy time shift and resource adequacy capacity. But there are other services available, and we can touch on where to find examples of that as we go through the presentation. And you can download the tool today. It's free to the public, open source. As I said, you can get the the user interface version of the tool, but you can also get the code itself and use it if you're an advanced user and want to integrate it into other things. And there's lots of reference case examples, a lot more than what we're going to talk about today in the New York long duration case. And there's also a lot of help. We have forums, places to submit your questions and feedback, how-to videos, the documentation, of course, and also a page there that talks about how to engage monthly with our energy storage integration task force, where we do, like I said, monthly web meetings to talk about the tool, how new features and highlight different ways to use the tool, and also get feedback from users in real time and integrate that as we continuously improve the tool. So with that, I'm going to pass it over to Miles Evans, my colleague, to start a live demonstration for you.
Sounds great. Thanks, Giovanni. I will share my screen as soon as I have the opportunity here. But in the meantime, I'm going to just give a quick intro to the case that we'll be looking at today. And the idea behind this case is to use some generic, non-vendor specific inputs to our tool to try to model an 8-hour duration battery. So, kind of bordering on the longer duration, the longer durations here. But it is still a battery. It's going to be a flow battery. So it has many, kind of similar characteristics to a, standard lithium ion battery. So what we're going to do is put these sort of generic level inputs into the tool, and we'll watch how that goes using the graphic user interface. And here we go with the tool right now. But as Giovanni said, all of the code for running this tool is available online for download. And quite a few people have valued a lot from downloading the source code, understanding how the tool works at a very low level if they want to go that deep below the documentation, and also integrating this tool with their own software, processes, automation, etc. So here is the graphic user interface for the tool. We have a lot of options here, but I'm going to just, instead of starting a new analysis or looking at one of the built-in analyses for the tool, I'm going to use an existing analysis that I set up before the case here for the webinar. And this is just going to be our demo file here. So I'm going to load that in. And because I saved it in the past and loaded it in now, we now have all of the inputs already ready to go. There are going to be some things here at the end. If we have time, we can do a comparison to a lithium ion type case that's very similar if we want to. But one of the things that it would change if we would do that would be how many years the technology would be around for, so the lifetime. That's one of the main inputs here. When we do these DER analyses that combine lots of different technology types, solar, storage, other generation, whatever it might be, all of those technologies can have different lifetimes. And so, even just setting the analysis horizon here is an important step And so for us, that's 20 years. We're going to just do a transmission connected standalone energy storage system here, which will model after a very generic flow battery. As Mike Gravely and Giovanni alluded to, we have a lot of other options for what we could do with our storage and other DER here, which we can look at a little bit now. One thing that does impact what we can do in DerVET with our system here is whether or not we need DerVET to tell us the optimal size for our resources. This is a feature in DerVET where we can include in an optimization problem the sizes of all of our DER. And for storage, that would be both the power capacity and the energy capacity of the storage system. This is a pretty useful feature for generating a sort of first pass assessment of what's the right size for a storage system, given the constraints that we'll tell the tool about and given the economic value of the system. For example, you could use this tool to determine the optimal duration for a storage system under an economic use case, or the minimum duration and power capacity for a storage system, providing a service like distribution upgrade deferral or backup power, microgrid. Those minimum sizes you can get out of DerVET for those applications as well. DerVET works by implementing and solving an optimization problem. And so to help save with computational intensity, we can break up our data. It does implement a time series optimization that tracks the state of charge of the storage systems over time. And in the graphic user interface, it's typically about a year of data that we give it. So we can break that year up into smaller chunks to help with the computational intensity. And in this case, we just broke it up into months. A month is plenty long enough for our 8-hour storage system to cycle many times. So it's plenty long enough to get a good idea of how the system should be operated. Every DerVET case requires knowledge of the value of energy because it's in an optimization problem. If we don't put a value on energy, then we often see just unrealistic results coming out of the tool, wasted energy, things that you wouldn't normally see, that kind of thing. And we can either collect that energy value through a retail tariff, power purchase agreement, or other fixed contract. And this would be what Mike and, or this would be the sort of thing where you could pull from a database that's integrated into DerVET if you had a retail tariff anywhere in the United States. You could search for that tariff and pull it directly in, or just create it manually. Both are options. But what we're going to do for this case is use some wholesale energy market results, some locational marginal prices from Long Island. And in a moment, we'll see where those get put in. But those just vary every time step, which is hourly in our model here today. So they change and are different every hour. We could also stack in flexibly any other number of services here. We have reliability, which is our microgrid service, which would provide backup power to a load during grid outages and have all the DER coordinate to serve that load. We could do demand charge management or some kind of aggregated demand response program participation here. We could also participate in wholesale services that are not just the energy market. So these are ancillary services like spinning and non-spinning reserves, regulation, et cetera. And the one that we are going to look at today is resource adequacy. And we'll see where we put in the inputs for this as well. But we'll just sort of model our storage system participating in the New York ICAP market for that. Distribution or transmission upgrade deferral is another option here. And then we have a flexible user-defined service as well in case none of these fit. We can definitely have a user create their own service and assign a value to it pretty flexibly there. After we've told DerVET the basic information about the project, how many years our analysis horizon is, et cetera, in the project configuration page, and we've told DerVET what our set of DERs here are going to do, we need to tell DerVET which DERs we're going to consider in our analysis. This, like the services, is designed to allow the user to flexibly combine different technologies. And you can see here we have some generation, some intermittent generation, energy storage, a couple of different kinds of electric vehicles, single electric vehicle or a fleet, and controllable loads. So demand response are all options that we can use for technologies in DerVET. In our case here, we just have a battery energy storage system, which is a flow battery that we're going to specify in a moment. Our energy storage system model here is quite flexible, and by tuning the parameters, it can be used to model other kinds of storage systems. But in particular for the technology options that are usually considered to be in the long duration storage area, there are some technical characteristics that might not be captured by our battery model. So those are an area of current development, definitely, but there's quite a lot that you can do with these parameters here. I'm sure many of you are aware of the Inflation Reduction Act and the standalone storage investment tax credit associated with that. One of the things that has come up in that process and is still being, I'm still learning about it, is how the maximum possible ITC benefit changes in response to things like whether or not the project benefits disadvantaged communities and that kind of thing. So this page here is only for California, and we implemented it because of the, for use in California projects. But this is the kind of thing that we could imagine becoming more important as time goes on here for the whole country. This is the CalEnviro screen results where we can put in a zip code in California and look up the CalEnviro screen score for the census tracts in those zip codes and understand how that impacts California-based policies and programs that could apply to the project. So this is the kind of thing that we've been looking at in California and might be more important nationwide in the future. So now that we know what we're doing with our DER, what DER we are implementing, we can now specify all of the data and technical specifications and things like that that go into our case. In our case, we have the technical specifications for a battery or flow battery up here. And the most important other inputs here are going to be the resource adequacy, service participation inputs, and the day-ahead LMPs for our Long Island case that will also play into the case. So clicking on the battery inputs, we can pretty quickly go through these, I think. The idea here is that we tell DerVET everything that it needs to know to make an effective model for our storage system. So in our case, we are looking at an energy capacity of 400 megawatt hours or 400,000 kilowatt hours here. And that is a known size, it's fixed. So we're not doing optimal sizing in DerVET right now. And we have a 50 megawatt power capacity, so a duration of 8 hours when discharging. We're modeling this after a generic flow battery. So we chose a round trip efficiency of 63%. This is again a flexible input. So if you have other storage systems, that can change, of course. And we're going to consider that the entire state of charge range of this battery is usable. So all the way down to 0 and all the way up to 100% with a target of 50%, just meaning that we'll start the year at 50% state of charge and end the year and every month at 50% state of charge. So we're basically saying here that we'll start the year at 50% state of charge, and all 400 megawatt hours are going to be usable to us. In reality, systems might be oversized in energy capacity, or limit the state of charge a little bit, state of charge range a little bit. So this is a way to handle that. We also have a self-discharge rate input here, which we consider for our case, to keep it simple, to be 0% per hour. So we're not self-discharging any, and in reality, of course, this would be some non-zero number for real systems. But for lithium-ion batteries, could be quite low. For flow batteries, could also be pretty low relative to their use case energy throughput. And that's not necessarily the case for every single type of storage out there, though. We have options to constrain cycling on our storage system, perhaps to comply with a capacity guarantee contract that limits cycling, or just to minimize the impact of degradation on a degrading battery. Which brings us to the next input here, which is whether or not we want DERVET to model degradation in our case. And this degradation is based on this degradation model here is based on a lithium-ion degradation mechanism set. So it implements, an approach that's commonly used for lithium-ion batteries. So we're not going to model that for flow batteries here, which degrade in very different ways, and with different outcomes. We also have auxiliary load, which also might be an important part of a flow battery case, but for simplicity, we've left that at 0 for now. Finally, we have capital cost inputs, fixed O&M cost inputs, and variable O&M cost inputs. The variable O&M costs do impact the optimization, so you can actually use this to suppress cycling and manage degradation in that way for lithium-ion batteries. And then a whole bunch of inputs here just relating to when we're building the project, how long it lasts, whether we replace it when it's done, the cost of replacing and decommissioning, and all of that is also handled here. Moving to the LMP inputs for our Long Island case, we just collect these in DERVET as a CSV file here. You can download a sample, put in your own data, and then upload that directly into DERVET. So these are Long Island LMPs from 2021. And as you can see, it has a little bit of peakiness in the summer here in August, but for the most part is a fairly tame LMP profile relative to other parts of the country, at some times anyway. For our resource adequacy service inputs here, we built this service explicitly to handle just how there are differences in resource adequacy procurement in different parts of the country. Basically, in a place like California, where a lot of resource adequacy needs are served through a must-offer obligation and just participation in the energy market, we wouldn't need a system like this that I've implemented here, where we put a hard constraint on the battery to discharge and be ready to discharge during the peak hours of the year. So that's all that this page is doing here, or that's most of what it's doing here, is just selecting a number of grid stress events, you could call them, that the system will definitely respond to regardless of energy price in a year. And we also give a capacity price input, again, just as a monthly CSV. Yeah, that's just the price input. Okay, so with that, we have the battery inputs, the resource adequacy inputs, the energy price inputs, and we don't really have much to do with the other tabs here. We could add an external incentive. I should note that in this case, I put in the standalone ITC value of 30%. into the costs of the flow battery already. So no need to add that as an external incentive here. And in particular, if I click on the external incentives window here, we can add an incentive either as a tax credit or as, just like a grant, basically some other incentive here. And that has tax implications. So we don't know that much yet about the implementation of the standalone storage ITC. So I just took that off of the capital costs instead of putting it in here. The other, sorry, there's something covering my window here. Okay, the other set of inputs here are miscellaneous. These are things like a discount rate used to calculate net present value, inflation rate, tax rates, that kind of thing. And these are not very important for our case for demonstrating the tool. So I'm just not modeling taxes right here, and I just have a generic discount rate and that kind of thing. Great, so with that, we are done defining our components. We get a summary page here where we can save our case for future use. That's what I did before this webinar and loaded it right in. And now that we're ready, I can click the green play button to run the tool. In this case, I think takes about 10 seconds to finish solving. So while this waits, I'll queue up the results here, which will start out with generic financial performance results and a heat map of how the storage system is operated throughout the year. That just gives us a very high level view of what the system is doing and how it's performing financially, given the costs and the benefits inputs that we gave it. And then we can drill down into really a graphical interaction with time step by time step level results, including how the storage system is charging and discharging, how it's participating in other services, if not just energy shifting and that kind of thing. So as we can see here with the 20-year life and the 2021 data that we gave the system, I should also note that the resource adequacy value I put in was sort of the maximum in 2021, which was $21 per kilowatt per month ish, with some decimals. We get these results. And the cost inputs for flow batteries are fairly uncertain and variable. So that's certainly an area where we could look at changing numbers as well. But in this case, just shifting energy and participating in the capacity market, we don't see a positive net present value. The costs exceed the benefits in this case, which is something that we could try to make up with other services like ancillary services or other programs or that kind of thing, distribution or transmission deferral, etc. Scrolling down to our heat map here of how the system was operated, we can see on the x-axis there is the day of the year. And on the y-axis is the hour of the day, where morning is at the top and evening is at the bottom. And yellow here is discharging, blue is charging. So we can see a fairly predictable pattern of the system charging in the very early hours in the morning and then discharging in the afternoon when the energy price is the highest. We can also drill down here and look at this sort of dispatch results in a graphical form that's like this, where time just goes along the x-axis, and scroll through weeks of the year here. I'm just going to go to some summer month. Let's go here. How about it's May? Let's go to June. So in June here, this is the week starting on June 5th. We can see the energy prices in orange here following their normal daily cycle. And then the energy storage charge and discharge power would be the purple line here. And so we can see it discharging at those peaks and charging in the early morning in the troughs, as you'd expect. And the state of charge of our 8-hour duration storage system cycles daily here, but less than a full depth of discharge cycle, and sort of declines throughout the week, which is behavior that we'd expect to see more and more of the longer duration the storage system is. We can align these with the heat map here of energy prices, which is the same as we saw on the inputs, but just a heat map form now, which confirms the afternoon highest daily prices here. We can also dig down into the financial results for each cost and benefit category here over our 20-year system life, net present or present value by cost category here. So we can see how much the capital costs are relative to the O&M costs, and then how much the energy benefit is from shifting energy down here in the brownish versus the capacity payments up there in the yellow. And similar to that, we have a pro forma here, which shows the nominal cash flows due to every service in every year. So you can go down here and take a look at very detailed results of what's going on. In addition to these, we also, when we ran the tool, have results saved that are saved on your computer, where you tell the tool where to save it in the first page, actually. I skipped over it. So these results are saved on my computer now in CSV form, so I can go make my own visualizations if I want, or interact with the results at a very, very low level to be useful there. So I think that wraps up the demo here. If we, not sure where I can go. I'm just going to stop sharing here if I can figure that out. And maybe we can go back to the slides for some Q&A.
Sounds good. Thank you, Miles. Can everyone else is welcome to turn on their screens for the Q&A if we're ready for that. Wonderful. Love this end part when we get to see everyone's faces. So the first question that we got for you all today, someone wanted you to comment more on battery degradation and other battery hazards.
I'll jump in briefly and maybe have Miles and Rom jump in as well. We look at degradation in the tool for conventional chemical, electrochemical energy storage, such as lithium-ion degradation curves, and we look at both cycling based on depth of discharge and keep track of that. And also calendar life degradation. And you can put your own specs in there for each battery, and that drives replacements as necessary across the life of the energy storage system. So that's one way. If Miles or Rom, if there's some other considerations you want to think about or discuss, jump in.
Yeah, so we have a bunch of different options for degradation in DERVET. Actually, they all require that we have knowledge of the cycle life curve of the battery, which expresses, how many cycles a battery can withstand at each different, depth of discharge bucket before needing replacement. One of the most common ways to use it, though, is to turn on degradation in DERVET and model degradation, but hold the energy capacity of the battery system constant over its life, to mimic a case where the system has been oversized so that it reaches its end of life at its rated capacity. That's another way we could model it in DERVET. We don't have to use it to actually reduce the amount of energy capacity available to the model if we don't want to, if that's not the case for modeling. And we don't have to use it to trigger replacements either. That could be handled outside of that.
Another thing which I'll add is, I think Miles did show that in the demo. So what we have seen in the projects recently is vendors give a performance guarantee for the life of the asset, as long as we keep the cycling to 365 cycles per year, or there is some safety limit guidelines that they set when they sign the when you purchase the battery or sign a PPA. So I think Miles showed in the demo that there is a cycle limit. So once you input a number to cycle limit, you constrain the number of cycles you perform. In other words, the battery only optimizes for those valuable hours where it sees enough value in terms of energy arbitrage or any other services that it has been contracted to provide. So that way we are mindful of the performance guarantee that the vendor has set forth as part of the project.
Great. Our next question asks, given federal funding to advance hydrogen, can we assume that electrolysis will be incorporated as a load flexibility enhancer for distributed systems?
I guess I can jump in and say that for sure, as Mike mentioned at the beginning of the presentation, we're looking at expanding DERVET to look at more and more long duration technologies and really dive into the nuances and constraints and benefits of each class of longer duration energy storage. So right now we kind of have the basics to do kind of the 8-hour kind of flow battery type technologies, and we want to expand as these newer technologies, longer duration, we start to understand how they'd be, their specifications and how they'd be implemented. That's something that we'll definitely be looking at in the DERVET tool. And on the distributed question, I don't see any reason why we couldn't look at it both centralized and distributed. Just thinking about the, all the same considerations as other energy storage of safety and footprint and all those things to consider.
Yeah, and I should clarify here that all the storage technologies we model in DERVET are electric energy storage that can both charge and discharge from electricity. So with a hydrogen-based electric energy storage system, yeah, we would expect that to be, part of the long duration DERVET modeling and able to be used as in one of the flexibility services, as you mentioned here, or distribution deferral or whatever it might have been.
Sounds good. For the batteries, do you all think that battery prices will need to come down for the cost benefit comparison to come more in line?
Go ahead, Miles.
Yeah, I mean, of course, as costs come down, the cost benefit analysis looks more favorable. There are plenty of applications though that we didn't look at today. We were just looking at a particularly expensive solution here, doing resource adequacy capacity and energy time shifting. So it didn't work out in our particular case, but there are a lot of applications that it probably could have, depending on what inputs we gave the tool. So and we know from the implementations that we're seeing that it is sort of the least cost best fit option in a lot of cases. That's why we're seeing more and more energy storage installed.
I would also add that the case that we showed, if we were doing this for a specific project and really, diving into it and looking at sensitivities, we would definitely also consider price forecasting in New York and specifically in Long Island to see, as offshore wind is getting developed, there's more capacity or transmission constraints, congestion, things like that to consider, and less conventional generation. We would work with other tools like production cost modeling and do iterative. We've done this in the past, do iterative processes where we look at the project level dispatch of storage, but also bring that back up to the system level and kind of harmonize those two based on the scenarios that we're looking at. So there's a lot of moving parts to consider, and when you actually get into a real project and trying to understand all the different options and decisions and sensitivities.
Does the model include issues like utility standby charges?
So yeah, excellent question. Yeah, as we all are aware, there's a ton of complexity in rate structures out there. So what we've done in the base model of DERVET, and in particular the graphic user interface here, is to implement a format for tariffs that is very flexible, but unfortunately doesn't capture every option. So what we've done, is implement this scenario where you can add an unlimited number of energy charges that vary both by month and by time of day, and demand charges that vary by month and time of day, can overlap, etc. So there can be, up to 12 seasons in our format, if you will, and up to 24 time of day rates in each one of those seasons, broken out by weekend and weekday and that kind of thing. But there are some kinds of tariff structures that we don't capture. So if they don't fit into that stacking and overlapping demand and energy charge format or fixed charges, then they're not part of the base model here.
Great. Someone asks if you can model the contributions of the Inflation Reduction Act in the DERVET tool. I know, Miles, that you had skipped over adding the tax incentives since we're not sure what the energy storage standalone tax credit will be like, but can you expand on that at all?
Sure. So we haven't, this is obviously very new, so there's no explicit handling for this act in our software. But we do have a flexible incentive input option here. So you could, for example, looking at a solar plus storage system, claiming the solar ITC in the past, you could, apply the year by year benefit from the ITC as an external incentive here for the first 6 years, I think. Of the project, capture when you no longer have restrictions on charging, that kind of thing, etc., as part of the services in DERVET, and put that in yourself. But for the Inflation Reduction Act, you'll have to do that process manually.
Yeah, and I would say that one thing that we're looking at here is maybe doing some analysis of kind of the impacts from a technical side and an economic side, and put out some some white papers on the subject using DERVET in the background to help us compare a lot of projects that had a hybrid component to take advantage of the ITC with storage, and now removing that constraint both for location and for charging. And not to say that hybrid systems still won't be relevant with the new ITC, but it just opens up more options and less constraints, I should say.
After California state incentives are integrated into the tool, can you share which states you're looking at to integrate their incentives next?
So the incentives input page on our tool is quite flexible, and we've constructed it so that whether it's a tax credit or some other type of funding, you can put that in yourself. So there's no limit here for what states are applicable to that. The tax calculations, at least for the federal taxes, will work out correctly, and then you input your own state tax rate and that kind of thing to handle the tax credit versus other funding and that kind of thing. So, for example, if we get a 30% of capital costs tax credit due to the Inflation Reduction Act for a storage system, all that involves is putting in a value that is 30% of your capital costs into that incentive window in DERVET, and same thing for any other type of state level incentive or that kind of thing. So I wouldn't be worried about the state level differences there.
How does this tool integrate with weather and climate modeling?
Yeah, great question. Right now, the main way that it interacts with weather and climate information is through the solar or wind intermittent generation resource that is modeled as part of this case. And for better or for worse, DERVET, we decided to not have a weather model intrinsic to it, or really even a like a wind production curve as a function of wind speed or that kind of thing. What we do collect is the results from an external model of your choice for that kind of thing. So you could enter into DERVET if you wish a bunch of years of real solar AC generation if you wanted to, and model each of those years as you wish. But that is the format that DERVET takes the information. So we don't do GHI, DNI modeling for solar, and we don't do the same for wind either.
Yeah, some things that we're looking at considering are temperature impacts from degradation, things like that during operations. And also where I think another place where it's a heavy driver for DERVET is in the price signals. So if you're doing those macroeconomics scenarios and doing like production cost modeling at a system level 20 years down the road, then of course temperature, weather, extreme events, things like that, all the different goals like decarbonization, electrification, that's where we would capture that as well. So it'd be a kind of a team of tools or a toolbox of tools where DERVET is just one of them.
Awesome. And completely switching gears, do you all have any comments on whether the open source codes are a security risk for power configurations?
For power configurations, well, so I actually think that the open source nature of the tool is it's the opposite of a security risk. The code can be examined by anyone and is found to be safe. When you run the code, you're running it on your local computer. So as long as you download it from the trusted source and install it yourself on your own computer, there's then no link to anything outside of your computer after the initial download of the installer or the source code, as you wish. So it's not like we're sending any information via the internet to some server somewhere, and there's no communication in the other direction either.
Super, sounds good. Safe platform to use, and then also just really great resources that you all have shared today. Since we are at the top of the hour, I'm going to ask Sam to bring up our next webinars that we're planning. There's 3 of them coming up. And while she's doing that, I just want to thank all of our presenters one last time for introducing the StorageVET tool to all of us. Like I had said at the beginning, we haven't gotten to all of the questions that you all have submitted, so I will send those along to the team at EPRI, and they might respond with written responses back to you individually. But like I said, we have 3 upcoming webinars coming up. The one in the middle is our next energy storage webinar. It's looking at 2 of our project teams, the lessons they've learned from the commissioning process. And then we also have one coming up next week, is it next Wednesday, a case study of a California congregation, and later in September we're looking at solar for manufactured homes. Thank you all so much for joining today. Sam, do you have any last notes?
Just to add that there's some contact information for the STAP team on your screen, and some more information about STAP, which is the project that hosted today's webinar through CISA, DOE, and Sandia. So thank you all. This was great. I really enjoyed learning from all of you, and we hope to see you at the next webinar.
Thanks, everyone.